Here. Okay. Something on design and validation of ultra-low fast transfer to the Sun-Earth saddle point with application to Visa Pathfinder mission extension. Again, 5 minutes when you are approaching.
Okay, thank you very much, and good morning. This talk is a little bit more applied with respect to the previous one, and it would be difficult for me after such a beautiful talk to talk about the work that we've been doing with ESA in the past year. This is about the possible applications for mission extension for ESA Pathfinder, and involves using ultra-low thrust propulsion, and involves exploration of the Sun-Earth saddle point that we will see in a second what it is. The work that I'm describing here has been funded by ESA through this contract, and I'm here on behalf of my co-authors Diogene Deitos, which is my PhD student, Mirko Rasotto from Dinamica, and Florian Rank from ESA ESOC. So let's frame this work in the proper context. The context is the dynamics of the restricted n-body problems, where the astrodynamics, I would say, where you want to apply the unique features that arise in this model. In this model, you have unique orbits because you have, like, for instance, Lagrange point orbits or ballistic capture orbits that you cannot have in the classic two-body problems, and you can exploit their benefits, for instance, the property of being fixed with respect to a pair of primaries, or the propellant savings, or the widening of launch windows, and so on. And these orbits represent a paradigm shift, at least for what concerns preliminary trajectory design, because the perturbations have to be leveraged, not cancelled. So all of these exist because of the perturbation. However, flying this kind of orbits is a little bit tricky, because in general space trajectories are not fully deterministic. You even don't know where the spacecraft is, because you have uncertainty in the states, you have uncertainties in the right-hand side, and whenever you perform a maneuver, you have an uncertainty in the performances of your thrust. So everything is affected by uncertainties. Moreover, these kind of orbits are highly sensitive to small variations in initial condition, by definition, I would say, because they use a highly nonlinear dynamics. And as we will see in a second, in the present case, we had the close to zero control authority, which means that we had very, very little control capability of our system. In this framework, there was a recent interest toward the saddle point. A saddle point is a point where the net gravitational acceleration between a couple of primaries, for instance, Sun and the planet, balance. This point has not to be confused with the Lagrange point, because in the Lagrange point you have a saddle point between among the potential of one primary, the other primary, and the centrifugal force. In this case, what I'm talking about is a saddle point only in the potential given by the gravitational accelerations of two primaries. So this is not an equilibrium point. You can only perform flight routes this. However,
Lagrange points, Euler points.
Excuse me?
There are Euler points, not Lagrange points.
Okay. Yes, they are Euler points, but yes, with Lagrange points, yes, the three collinears are Euler-Lagrange points, and the two triangular Lagrange points. Yes, thanks. Anyway, because of their property of having zero background accelerations, they are ideal location to perform a number of experiments. For instance, they are ideal location to test possible deviations from the general relativity. Here, I don't want to embarrass myself in talking about something that I'm not expert, but the idea is to that ESA wanted was to perform a test of MONT, which stands for modified Newtonian dynamics, because you need this level of acceleration, less to tend to understand. Anyway, there are, for every sun-planet system, there is one saddle point. The closest one and the most reachable one is the Sun-Earth saddle point, which lies at approximately 58,000 kilometers far from the Earth, between the Earth and the Sun. So this means that the point is within the orbit of the Moon. To perform this kind of test, ESA Pathfinder was already in orbit until a few weeks ago, actually, and it was orbiting Sun-Earth L1 here. The key point of LISA Pathfinder is that it has a very highly sensitive gradiometer here, made by two free-falling masses. And the idea was to use this precise accelerometer to measure the acceleration when flying through the center point. So the idea was before displacing LISA Pathfinder was to get from the Sun-Earth L1 to the Sun-Earth saddle point and perform this kind of experiment. However, the only point is that this giant chemical module was ejected from the science module, which is this one, the yellow one, soon after the launch. And the only possible ways to control the LISA Pathfinder trajectory was using these cold gas thrusters. These cold gas thrusters, they deliver 100 micronewton of thrust over a 500 kilogram spacecraft, which means nothing. The thrust to mass ratio in this case was 10 to the minus 7 meter per square second. Consider that whenever you have low thrust acceleration, usually this ratio is about 10 to the minus 4. So it's 3 orders of magnitudes less than what current technology can deliver. And the total delta V budget here was around 1 meter per second. So we were performing emission analysis here with a total delta V budget of 1-2 meter per second. Usually you have kilometer per second when doing this kind of stuff. So this tender was issued, and it was awarded by Politecnico di Milano and Dinamico, which is, by the way, a spin-off company of Politecnico di Milano that I co-founded a few years ago. And there were 2 parallel contracts. The other contractor was Astrum Defense Space. The idea was to study low thrust, ultra low thrust propulsion with low delta V level with this kind of spacecraft, and to how to accurately design and navigate in this region of the space between L1 and L2, Sun, Earth, and Moon. This was the title of the contract. So what did we do in this kind of study? We actually divided the study into 3 main pillars. The first one was the design pillar, where we developed sophisticated methods to design this kind of transfers to the saddle point. Then there was a big part, which I'm not unfortunately talking about today, that was about the assessment, how we implemented navigation, orbit determination, sensitivity analysis, and so on, to validate the feasibility of this kind of transfer. And the application then was the third pillar, the application to LISA Pathfinder. We ended up by byproduct of all of this in developing a general purpose software that does all of this. It's called the Ultra Low Transmission Analysis tool, and it's been delivered to ESA last week. So the solution life cycle here, in view of all of this, was to design the trajectories and have the preliminary solution. After the preliminary solution, perform a preliminary assessment, geometric and sensitivity analysis, and to have candidate solution, and then to accurately perform knowledge analysis and navigation cost on this solution to have what we call feasible solution. As I said, because of lack of time, I'm only talking about this block here, which is the trajectory design, which itself was subdivided into 4 more phases, which we call exploration, optimization, Finite-burn, and refinement. Here we are talking about orbits that needs to fly the saddle point with high precision. The requirement was to hit a bubble center at the saddle point with radius 50 kilometers. So the requirement was very high, therefore the modeling has been very accurate for this kind of model of problem. The model that we used was our own implementation of the rotopulsating restricted n-body problem. In this model we have the Sun, all of the planets, and our Moon, the planets with the barycenter. Moreover, we have the solar radiation pressure and the J2, and this model is written in a frame that rotates with the Sun and the Earth, not uniformly, because in the real n-body problem this is not the case, and also pulsates to adjust the distances. This model was tested with NASA's GMAT with very nice results, and it's full ephemeris model, therefore the position of the planets are extracted from spice. It's all spiced, this kind of thing. So these are the equation of motion. Rho is the spacecraft state. C is a transformation matrix. K is a scaling factor, and tau is the independent variable here. In the exploration, the initial idea was to get familiarity with this kind of problem. So what we did was to perform a direct numerical simulation campaign to get familiarity with the problem and to understand how this kind of dynamics is. So the problem is to go from this orbit. This is the Earth here at around 1. At 0 you have the Sun, and this is the equivalent of the orbit where Lisa Pathfinder was. And we had to go from this orbit to this point here, which is the saddle point. Okay, so we performed as I said, a numerical simulation campaign, and by varying out of plane amplitude of the Lagrange point orbit, phase of the departure phase of on the orbit, and initial phase of the Moon, we were checking the saddle point missed distance, the time at saddle point passage, the number of lunar gravity assists, if any, the minimum distance with the Moon, and the time of the Lagrange of the lunar gravity assist. This is because here we were already using the instability associated with this kind of orbit, because with only 3 centimeters per second you can inject the spacecraft toward the unstable manifold associated with the L1 orbit. And we were doing a number of cases. The most important one was to see if with 0 delta V, with 0 deterministic delta V here, we could reach the saddle point. So we performed a number of simulations. Of course, here we have no time to show the results of a 1-year contract work, but here I'm showing also one out of the 6 cases. For what concerns L1 and 0 delta V, we try to summarize the results in this scatter plot, in which you can see the cross relation between the 3 input variables, out of plane amplitude, initial epoch, and time on the periodic orbit, and the output variable, which are minimum saddle point distance, times at the minimum saddle point distance, number of gravity assists, minimum distance at the gravity assist, and time of this. And here the color code is that blue is 1 saddle point passage, red is 2 saddle point passage, and so on. This is because ESA wanted to perform 2 saddle point passages to avoid false positives. So here we can see a number of features. For instance, that many short-term solutions exist, less than 1 year to reach the saddle point. If you want to, of course, perform 2 saddle point passages, you need to wait a little bit more. Many lunar gravity assists are not as important, because even with 0 lunar gravity assist you can get. Of course, if you want to get 2 or 3 passages, also you need to account for a number of lunar gravity assists, but this is not strictly required. The solution is spread all over the distances, because at the beginning we thought that you would need a very close passage to the Moon. This was not the case. What is important is to get the perturbation of the Moon, but not a strong deviation of the orbit. And this is important because small halos, this is the AZ is the out-of-plane amplitude. Small out-of-plane amplitude is better, because the less out-of-plane motion you have, the more chances you have to get to the saddle point, because by definition the saddle point lies in the Sinai plane. And so on. This is also important. The departure epoch, here we have an hole. The departure epoch is coupled, it plays a role, and plays a role especially when you couple it with the phase on the departure orbit and the phase of the Moon. So you cannot arbitrarily leave this orbit at any time you want. We performed this campaign in the synchronized 3-body problem, restricted 4-body problem, rotopulsating restricted n-body problem. And we saw that the Moon perturbation here, which is not there, enables some multi-saddle point passages that were not there, and also increases the chances to have a passage to the saddle point. In general, in a high fidelity model here, the chances to passage to the saddle point is a little bit less likely than in the 4-body problem. So these were solutions that only passed through the saddle point with less than 10,000 kilometers distance, but the requirement was to hit the saddle point with many orders of magnitude less. So what we did, we used this as a preliminary solution, and then we ran a fully trajectory optimization algorithm. So we implemented a multiple burns, multiple arcs, multiple shooting, and we had a number of maneuvers divided into segments and so on. This was transcribed with the variables that are the states at each node and the times. This is the objective function was the square of the delta V, and then we had a number of equality and inequality constraints. Worth to mention is the last one, the last inequality constraints, which accounts for the time needed to spread the delta V over a finite-burn arc, because this was already accounting for the next phase. These are examples of solution from here. These are two passages from here. You have a number of arcs here, and you have first and second passage. Here is another two-passage solution, but in any case, the delta V was already high, 7 and 9 meters per second in this case. So because of this ultra-low thrust propulsion, we need to 1 meter per second can be done with this kind of thrust to mass relation by thrusting for almost 6 days. Okay, so impulses are not well accurate enough in this kind of model, so we need to spread the delta V into a finite-burn maneuver. So we have this continuous thrust formulation where you have T maximum, throttle factor, thrust pointing angle, and the spacecraft mass, and also in this case you have to account for mass variation of the spacecraft. The idea was to convert, if this is the orbit before the impulse and this is the orbit after the impulse, the idea was to find the initial time here and the final time there, and a certain thrust pointing history such that if you start thrusting here, at some point you will get the same orbit as in the post-impulse case. And this was a problem of finding 2 times and 4 times 2 coefficients, because we used third-order polynomial representation of this. And these are finite-burn solution. Here you can see the length of the burn here. These are in the full model. In this case, we have less than 1 meter per second. In this case, you have 0.2 meter per second. So it's in principle feasible. And here you have another example of minimum time of flight where you need 3.5 meter per second, but only 100 days. And this is the maximum time of flight with 1,000 days that we found. So we implemented another module called Refinement, because for implementation issues we had to do all of this in the J2000 frame, but when rotating the initial condition with a slightly different right-hand side, which models the same effects, the saddle point was missed a little bit, so we performed an identification and a tuning of the angles to get a precise hitting. And this was we found out of all of the direct numeric simulation that we ran, we found 39% of solutions which are good candidates, and from L1 and from L2 only 10% of solution. Then we had another big block of work that was done, which I'm not presenting unfortunately because of lack of time, but the idea was to assess the feasibility of this. So we implemented knowledge analysis, sensitivity analysis, to understand also how much does it cost to navigate on this kind of orbits. And then the idea was that after the knowledge analysis, this was your nominal state, this is your dispersion here, this is the saddle point, and this is a sphere of radius 50 kilometers. So if this happens, is that the orbit is feasible, the transfer is feasible, because this is a 95% ellipsoid probability. If this is inside the sphere, then it means that and this is what we did. So this is the knowledge analysis. This is how the position knowledge evolves when you have the transfer. These are the thrust arcs, and whenever you see the lines that go down, it means that there is a measurement done by the ground station. So we also implemented the radiometric measurements and the orbit termination cycle. So I'm skipping to the conclusion, just saying that we found a feasible application for LISA Pathfinder. Unfortunately, this was not implemented because ESA already decided to dispose the spacecraft, but we found a feasible application. This was the case that we presented. This is the knowledge analysis in position and velocity. This is the navigation cost, which could have been reduced by reducing the initial dispersion. And in conclusion, let me say that what we found is that going to the Sun Earth saddle point is more likely from L1. This is, we thought, due by geometrical reasons, because the saddle point is already to L1. Very low delta V exists, and very short duration transfers exist. For what concerns flight dynamics, there are a number of considerations, and also there was evidence of feasibility of these Pathfinder transfers. These saddle points are, for me, were new. I only was aware of them a year ago at a spaceflight mechanics conference, but they are quite interesting and quite unexplored, so there can be a number of strategies, either opportunistic mission or dedicated mission, to explore them. And with this slide, I'm listing a number of few references that can be used. Thanks for that.